Hello everyone, welcome to the sixth session of 2024 SPE Europe Energy GeoHackathon. Topic of today's bootcamp is Leapfrog software. Our presenter today is Josh Sellars, project geophysicist, Vancouver, Canada, specialized in geophysical processing, interpretation, modeling for energy exploitation and feasibility studies. Current role, project geophysicist for Leapfrog users in North America. So before we give the word to our speaker today, I just want to recap. Please, if you have any questions, post them into the chat. They will be addressed after the session. And also, please do not try to disturb the course of the session. Thank you very much. Josh, the floor is all yours.
Thank you, Pavel. So today we're going to be doing a quick overview of Leapfrog. Leapfrog is a commercial software that enables 3D visualization, geomodeling, and interpretation of data in 3 dimensions. So Seequent has provided all teams who register for this bootcamp access to a license of Leapfrog. I don't think that the licenses have actually been activated yet, but once the bootcamp, once the challenge does get up and running officially, you will have access to this. It's a great tool for interrogating and interpreting your data in a geospatial way. So today what we're going to do is I'm going to go over a quick review of the data that we're going to be working with, plus the challenge at hand. And then we're actually going to break out into the software, and I'm going to show you how you can utilize the software that you have access to do some really cool things with your data. Before we do actually jump into the software as well, we're going to review some global case studies of how Leapfrog has been used in commercial exploration projects. So this is a quick overview of the second session that myself, Mike, and Boris hosted. The challenge, a quick introduction just so we all remember exactly what we're doing with this SPE GeoHackathon. So we're going to be using a data set from Croatia, and I will show you how that looks within this 3D dynamic environment. Although we will be utilizing Leapfrog for visualizing and QCing the data, the main aim is to use machine learning to predict reservoir properties for 2 wells. And we're going to do that by using existing drilling and seismic data from 6 other existing wells. We're going to utilize the information on the 2 wells that we predict to generate a geothermal field development plan to generate electricity for a town of 50,000 people. So it's quite an interesting project, but that is the entire scope of the SPE hackathon. But today we're going to be focused on how to utilize this 3D modeling tool to QC and interpret your data. Some of the deliverables include a workable code with sufficient comments so that the judges can reproduce your results, short 4-page high-level management report, and for data analytics to describe what you did. What's really important for this session is to make what you can focus on for this session is making a 5-minute video presentation of the project. So the tools that we'll look at today can be used to communicate the results of either your machine learning code or the other predictive algorithms or just interpolation algorithms that you can utilize within Leapfrog. Quick data review. So I'm going to show you how all of this works within this application: maps, seismic lines, petrophysical data, drilling information, and we won't actually cover geothermal gradients today, but we will look at some ways that you can create temperature models in 3 dimensions. And again, the software that we're going to be focusing on today is Leapfrog. And another quick overview for visualizing well and seismic data. So a brief overview of Seequent as a company who provide the software called Leapfrog. We're a world-leading coupled modeling software, and we provide modeling software to address the challenges of exploring and exploiting for geothermal assets, utilizing mainly software that that handles geophysics, geology in Leapfrog, reservoir engineering in Balsam, and a cloud-enabled model and data management solution that connects these applications together through Central. And this is an image of a conceptual model linked to a reservoir model. So we can forecast, we have other products that will enable you to forecast the geothermal and electricity output of your reservoir over time, depending on different exploitation, production, injection phases. The software that we will be focused on today is Leapfrog Energy. In the top right corner, this is an example of a research project called the Utah Forge project that utilized Leapfrog for planning their drill holes, creating temperature profiles, and incorporating seismic and DFNs into their projects. The exact same process that you'll be focused on using this data set today is used widely throughout the industry and research institutions. So we'll be building a 3D conceptual model of a geothermal system, QA/QC, machine learning, deliver project properties and update our geomodel, and visualize and present results. So this is an example of something that we can create in Leapfrog. It's another image from the second session that we looked at. This is the temperature profile from the 3 different wells that we had temperature logs on. And this is an updated 3D geologic model. And combining these two, we can start to create hypotheses about what's actually going on in the subsurface, being able to visualize, spin things around, and interrogate things in 3 dimensions. Throughout the course of this session, I'm going to take you through the process of not only importing data to create objects like this, but the process of actually creating objects and creating multiple iterations of those objects. So Leapfrog fits into the geothermal life cycle throughout the entire discover, design, develop, and operate phase. As a geologist in industry, you're constantly updating your conceptual model based on additional information from drilling information, and also information that you take from the field. You're constantly communicating with your geophysicists, your reservoir engineers, in a way that is visual, and so that you can kind of connect the dots between each different persona and phase of the geothermal life cycle and development. Before we crack into the actual software, we're going to go over some global case studies. We've got a couple in the United States, Iceland, Spain, Japan, and Indonesia. This case study from Japan, field optimization from Yamagawa, Japan. This is actually quite similar to the process that you're going to be working on today, where they've incorporated information from geology, geophysics, temperature, and in this case, alteration. So they use that to create, in the top right corner here, a conceptual model about their resource. They use the seismic data to determine the extent of the confining impermeable unit. They incorporated all of their drilling information, seismic data, and preconceived information about the temperature profiles in the subsurface, and they evaluated that onto a geocellular grid. That simulation grid for the field was then used for forecasting for a new binary power plant, which was under construction. So they used all of this information within Leapfrog to forecast the potential power production of their geothermal resource. Another example is this large data set integration in Helsinki, Iceland, where we've got over 70 deep wells, which include lithology, secondary mineralogy, geophysical logs, and different well designs. So they found in this particular example that there was a good correlation between resistivity and alteration mineralogy, which is used to infer the lateral extents of the clay cap, which is the theorized top of the geothermal resource. So they used this 3D model for well planning, and as they drilled new information, they continuously updated their conceptual model, which then allowed them to better predict the potential properties of the subsurface. Another quick example, and we'll probably just look at this one and then crack on to the actual software itself. But this is an example of a regional scale conceptual model where they're looking at where they're focused on defining the extents of a sedimentary basin in Spain. They used publicly available information from surface, cross-section, geophysics, and borehole data. And they are taking the results of this volumetric interpretation and evaluating it onto a discretized flow simulation grid for called FEFlow for additional resource assessment. This particular example, it's good to note that it is using a lot of publicly available information. So if you are currently working on a master's or PhD project or any kind of research project, there is a lot of public information that can plug directly into Leapfrog to create these 3D representations of the subsurface. So if that is of interest for your particular projects outside of this GeoHackathon, please do reach out and I'd love to discuss more. So with that, we'll probably jump into the software. And we gave a quick introduction to the software in the second session, but I realized I went quite fast because it was a quick introduction. Today is going to be a more guided learning session. Although you don't have access to the software yet, I will keep the pace under control because this video will be recorded, which you can always look back on while you're actually performing the interpretations for the SV hackathon. So I do apologize if the pace is a bit slower. If it is too quick, Pavel, and you think I'm going too quick, feel free to just tap me on the shoulder and get me to slow down because I've been known to go a bit quick sometimes. So with that, I'm actually going to switch screens because I realize the text is probably a bit small on this one. So I'm going to jump down to my other screen and I'm going to reshare that. And Pavel, could you just give me a quick holler once you are able to see that new screen?
Yeah, it's there.
Sweet. Perfect. All right. So a quick introduction to Leapfrog Energy. I'll give you a quick overview of the user interface first. On the left-hand side here, we have the project tree. Leapfrog is a 3D application which we've designed to be as intuitive as possible. On the left side, the project tree hosts folders. These folders host the data sets that you'll be working with in 3 dimensions. Leapfrog is not a menu-based application, so all of the menus, quote unquote, that you'll see that you'll need to import data and to run additional processes on that data can all be found underneath the project tree. So if you wanted to import well data, you can simply go to the project tree, look for the folder that represents the type of data that you wanted to import, and you can right click and then you'll have some options for importing that data. The same if you wanted to run additional processes on the data that you've imported into your project tree. If you wanted to run those additional processes, you simply right click the object that you've imported. So for example, if you wanted to import 2D SegWi files, which you'll have access to in this project, you can go down to the geophysical data folder, which is representative of seismic data. You can right click the geophysical data folder and you can import 2D SegWi files. If you needed to run any additional processes on those SegWi files that you import, you can simply right click on that particular object. So that's the project tree. It's the portal for importing data into your project. It also hosts all of the data sets that you can then run additional processes on those data sets by right clicking the particular object. We also have this 3D scene, which is here in the middle. This is where you can actually visualize and interrogate the objects that you've imported into the project tree. The 3D scene, you can access and visualize a lot of these objects under the project tree simply by dragging and dropping. So left click, drag, and drop. You can drag and drop multiple objects at the same time by left clicking, pressing Shift or Control on your keyboard, selecting multiple objects, and dragging and dropping. Any object that's accessible by this 3D scene is now available in what we call the Properties panel, which is directly below this 3D scene. This is where you can define how objects are visualized. So we see this drilling information with lithology logs here in the middle of the screen. If you wanted to turn on and off those particular logs, you can simply press this eyeball button. If you wanted to remove these logs from the 3D scene, you can press this X, which removes them from the scene. We can also change and edit the transparency of objects. And for data sets that have some sort of numeric values, we can left click on the object that has a color ramp, and we can either adjust an existing color ramp or add a new color ramp. So this properties panel allows you to define how objects are visualized within that 3D scene. Oh, sorry, this is the shape list. Shape list. The properties panel is directly to the right of the shape list. So any object that you select in the shape list, which is highlighted by blue, so left click, this will open that object in the properties panel. And this is where you can run additional filters and processes to, again, optimize how these objects are visualized within this 3D scene. So, for example, this geophysical data, because it has numeric values associated with it, we can enable a filter, and we can filter information based on this, this slider right here. So that's this geophysical data set. In the bottom right corner, you have the ability to stretch or compress the z-axis. So if you left click the bottom right corner, we can change the z-axis back to the default of 1, or if you're working on a large area like we are today, and you wanted to increase the vertical exaggeration to see more differences, but as we go through the through the z-axis, you can also stretch the z-axis. One incredibly useful tool in Leapfrog is the ability to draw a slicer, and this allows you to step through the model in space. This is a great visual QA/QC tool. It's also very great for optimizing the view into your project for screenshots or to create videos to present your findings back to the group. So again, it goes back to the ability of using Leapfrog as a 3D presentation tool. If you wanted to clear all of the objects from your 3D scene, you can either clear them all individually by pressing these X's in the shape list, or from the 3D scene, which is again this 3D object in the middle. In the top left corner, there's a little garbage can button that allows you to clear the scene. This garbage can button doesn't delete any of the objects from your project. It simply removes them from the 3D scene. So we can clear that scene. I've already created a very simple geologic model, which is going to be included in the package that we release. And I'm also going to display the data that I've used to create that geologic model. The slicer is an incredibly useful QA/QC tool, but again, also very good for creating presentations. To draw a slice, use the little knife button in the top middle with a line underneath it, and this allows you to draw a slice through the objects that you see on that 3D scene. Using the period and comma button on your keyboard, you can step through your model in space. So we can zoom, pan, rotate, and step through our model in space. We can also change how this slicer is defined. What's more important though, or what is equally as important, is the ability to define how each object interacts with the slicer. So we've got these volumes that are associated with different rock types. We can display the legend right here to show these different rock types. If we click on this drilling information, we can define how this object interacts with the slicer. So if you click on your drilling information, go over to the properties panel, we can define how this object is sliced. So we can say unsliced, and now we can see the raw data that's been used as an input into creating these interpretations and the actual interpretations themselves. So this is one of many ways that you can use the slicer to interact with QC, and also present the interpretations and objects that you have associated with your data set. Okay, so before we actually are able to work with the data within Leapfrog, we have to make sure it's in a Leapfrog compatible format. So in the data package that will be released, will include the cleaned up version of the drilling information, a topography grid, a shapefile that shows the outline of your seismic lines, a few maps that show aerial photos and also the extents of your project, a semi-completed Leapfrog project, so you don't necessarily have to worry about all of the importing, and some 2D seismic lines that cross some of your drill holes. We'll also provide a zipped folder with the original papers from some of those case studies that we discussed at the beginning of the call, and also the PowerPoint that we've referenced along with this Leapfrog geosurface types. So one of the most important objects that you can visualize within Leapfrog is your drilling information. If we look at the wells folder and the official files, we have these 5 different files that we can use to construct and create 3D well log interpretations. To create these 3D drill hole objects within Leapfrog, we do need it in a specific format. Generally speaking, you will need a collar, a survey, and some sort of downhole interval or point information. So the collar in this case, this locates the piercing point associated with your project. This shows the XY location at the surface of your well. It's basically a singular point that shows the top of your drilling information. We also have a survey file. This survey file constructs the 3D well trajectory. In this case, they're all vertical wells, but if you had a deviated well, this survey file is critical for defining that 3D well construction. The survey file pulls information from the collar and constructs a 3D version of the drilling track. We also have some downhole numeric and categorical information as last points and geology strat simplified. So we've got downhole information that shows us information about the log lithology values that Boris has done an incredible job in simplifying for the group from a lot of legacy drilling reports. We've got these 7 different lithologies that we've intersected with our drilling information. Each one represented by the color that we see in this legend. We can also showcase the actual log lithology by pressing this little A button. We've also got some point values that are representative of logged physical properties. So we've got a ton of different logged geophysical data sets, including caliper logs, neutron porosity, density, gamma ray, some permeability calculations, spontaneous potential, and temperature or specific resistivity, sorry. So one very important aspect of this project is obviously going to be temperature. We can visualize temperature logs in a similar way that we were visualizing, or we can optimize how we visualize temperature logs in a similar way that we were visualizing the different objects on the slicer. So if you drag and drop the temperature logs and you wanted to communicate that the temperature is increasing as you get deeper, you can click on the temperature logs, and in the properties panel, we can change the radius values so that it's reflective of the temperature values. This is also going to allow you to start to visually QC these objects. So in this particular well, you might want to remove these 2 values because they seem to be outliers in this particular log. The other 2 look quite good. So again, it's utilizing Leapfrog to visually determine outliers and also potentially spot some trends associated with your data. Within Leapfrog, we can also visualize some topographic information. So this is the extents of our project area, where we've got a draped map on topography that show the box associated with the project area that we'll be working on. We've got different seismic lines that cross particular drilling information, and we've got these two boxes. We can define this by either the entire project extents or a particular area. It's really up to the attendee how they want to split this up. We've had multiple different Drape GIS objects, including the original seismic shapefile lines. We have an aerial photo that shows the extents of the project area, where we've got some towns and some farming fields, as well as some mountains in the top right corner. And we've also got the road information associated with this project. So we've got these 6 drilling traces with log lithologies and varying degrees of logged geophysical data sets, or logged last data sets. And we've also got these 2 planned wells, and I use the planned wells folder because this is going to allow you to evaluate the interpretations that you make in 3 dimensions onto the trajectories of these 2 unknown wells. So going back to the purpose of this project, we're looking at predicting the properties associated with unknown well 1 and unknown well 2. So I've created these under the planned wells folder, unknown 1 and unknown 2, and this is going to enable you to evaluate your 3D interpretations and interpolations onto these data sets. Before we actually get into the 3D modeling space, I'm going to take you through in detail how to import and visualize your drilling data sets within Leapfrog. So although you will have a project that has this information available, you will also have access to a bunch of legacy reports associated with each drill hole. So although I did do some of the work to QC a lot of the data sets and make them into a Leapfrog compatible format, there is additional data available. So in each one of these drilling object or drilling folders, you'll have multiple different LAS files. You'll have some legacy reports, which you can again get some additional information from. And you'll also have some images of well logs, which I did not digitize. So if you have the ability to digitize those using some sort of machine learning algorithm, that would be incredibly useful in this case. But to import the drilling information that I've QC'd, you can simply right-click the well data folder, go to Import Wells, choose Local, and then we're going to import our drilling information. Like I mentioned before, to import and construct these 3D well trajectories, you do need a few different files. The location, again, is going to be the point on topography that locates the top of your well in 3D space. The survey is going to construct the 3D well trajectory. Intervals and points are simply categorical or numeric information that's logged as measured depth along the drill track. So let's look at what those actually look like. If we wanted to import the collar or the location associated with our drilling project, we simply press this Browse button, the little folder on the right side, and we'll choose our collar or location file. It's a semi-smart importer, so it will sometimes automatically associate the particular, or sorry, objects with the correct names to import directly. In this case, actually, we're going to leave out the geology file, so we'll remove that one. And now we'll look for the survey. So we'll press the folder, and we'll choose Survey Div. For intervals, we're going to import the wells geology strat simplified. This just has additional information from the original geology file that we were just looking at. And we'll also import points. So we'll import these last points. So we got our location, survey, intervals, endpoints. So these objects are all relational databases. They will have a column that shows a whole ID, which allows you to relate all of these different objects together. So when we press import, it's going to be step 1 of this import dialog. So I'm just going to repeat that. So we'll go caller, survey, geology, and last points. We press import. The caller or location file has 5 required columns. We have a whole ID or well ID. So this is the relational portion. You'll notice that each object has a similar well ID. The name associated with the well ID file right here, so Vera Vitica 1, let's say, for example, this naming convention has to be consistent through all of the downstream objects. So your survey and your interval and your points files all need to have the exact same naming convention as the well ID that's within your caller. So we've got a total depth associated with, or max depth associated with each drill hole object. We've also got an X, a Y, and a Z. So this locates the top of your well in 3D space. Generally speaking, it's going to be essentially at topography. So your location has these 5 columns, mandatory. We'll press next, and then the next stop is the survey file. This constructs, again, the 3D trajectory, where we need to define the well ID. Again, this is how the relational database works. The caller locates it in space. This survey creates the 3D trajectory from that point in space. So we've got an azimuth of 0, an inclination of 0, and a depth of 0. All of these zeros essentially create vertical wells. If you had a deviated well, you would notice that the azimuth, inclination, and measured depth would be populated with much more information. And we'll press next. And now we come to our first interval file. So this shows categorical information associated with a measured depth interval along the well track. So in this case, we've got from to. This defines the extent of this interval, and I apologize, I didn't realize that they were on different sides of the spreadsheet. So from 0 to 15, we've logged all of this information about the lithological information. So we've got a strat simplified column, strat simplified bureau, and a stratigraphy column. All of these are very similar but slightly different. Again, Boris was able to do a lot of the QC work and simplify a lot of this lithological information associated with your projects. So this is how an interval table within Leapfrog is constructed. We've got a measured depth and an interval associated with those measured depths and some sort of categorical or numeric information. Similar to the survey data, every single object needs to have a well identifier column, again, to establish that relational database connection. So we can import all columns in this scenario, and lithology and category essentially work as very similar column types. So we can either import all columns, or each one of these particular columns, we can left click and we can define how each object is imported. On this quick call, we probably won't have time to review, or sorry, in this probably like hour-and-a-half session, we won't have time to review every single thing within Leapfrog in detail, but you will have access to a an online training manual that will take you through in detail a lot of these different processes. So we'll choose category for each object. So we've got lithology, strat simplified baro, and stratigraphy all imported as category. And most importantly, we have this well identifier. We'll press next, and now we've got some point information. So this is our kind of last logs associated with downhole physical property logs. We've got multiple different columns associated with these different properties. We have a depth. So this is a point file. So instead of having an interval with a from to column, we have a singular depth. And this is basically a singular point along this well track. Here logged as measured depth. We've got a hole ID, well ID, which is the well identifier. Again, the relational database that allows you to locate the measured depth along the 3D trajectory defined by the caller and survey file. In this case, we can also import all columns, but for this particular object, because we have a lot of points, there's some of these columns that don't actually show up any points on the preview rows, so we do have to manually make sure that these are imported as numeric. So on the column summary, we can simply choose each one of these objects by left-clicking, pressing Shift, and then importing these all as numeric. And once that's finished, on the top, we have a processing log where it shows the process of the import associated with the caller, the survey, the downhole intervals, and the downhole points. So as you continue to make changes to your project and you may need to reload or create new drill hole objects, this is a way that you can do that. And if we wanted to just quickly visualize this information, we can see the last points associated with our object. We can see the traces associated with the drill hole objects. And we can look at the simplified stratigraphy also. In this particular example, we have defined colors for each different stratigraphic unit, which we can see from this object right here, where we've got these different names associated with different colors. We've also provided that within your data package, or we will provide that within your data package. So the strat simplified column, which is what we'll use to build our geologic models, we can right click and go to colors and import, and we can import the predefined strat simplified .lfc file. And just in case I went too quick there and you're watching this recording, I'll repeat that process. We can expand that out, right click, strat simplified, go to colors and import. And we can import the colors that I've defined in this working project. Perfect. So I'm just going to delete these because we're actually going to be working off of the data that's already been imported. So I'll drag and drop my strat simplified into the project. And the next step in this quick journey of learning Leapfrog is going to be to construct a 3D geologic model. So again, Leapfrog is quite an intuitive software. If you wanted to construct a geologic model, you simply go to the project tree, you scroll down until you find a folder that is representative of the type of object that you want to create. So we can right click the geological models folder and we can press new geological model. Leapfrog is quite a unique application because we are constructing gridless geological models, and we discussed this in the second session. Well, the objective here is to construct surfaces that represent geologic contacts, which then get activated, which construct volumes. And one of the advantages of utilizing Leapfrog, especially in a geothermal environment, is it gives you the flexibility of constructing the types of geology that you want. Because we're not constrained to a predefined geocellular grid, you can create curved surfaces. You can manipulate those curved surfaces based on seismic interpretations and your own manual interpretations based on the type of geology that you're actually trying to represent. Under the topography folder, we've also got the project map. And we've got two areas, this one on the left and this one on the right. This default boundary that you see constructed, this gray box, this is going to be the boundary of our geologic model. This is where the extents to which our surfaces that we generate will be continued to. For our project, we likely are only focused on a particular area, so we can shrink the boundary associated with our project to this particular area. So we can use these arrows on the top and bottom to match with the extents defined by this pink line on our map. And you can expand it out a tiny bit, or you can match it exactly. We can also extend the bottom of our model to match with a particular depth. So this is good for this particular object, and we can also input the exact easting, northings, and elevations of the boundary of our geologic model. The base lithology column, this is going to pull information associated with the categorical information that we define as the base lithology. For this project, we're very likely going to be using the strat simplified lithology column, which is going to pull information associated with these objects. So under base lithology column, we can change from lithology to strat simplified. The surface resolution, again, we're building surfaces that represent geologic contacts. So the surface resolution is the size of the triangles associated with the surfaces that we're building. So we can decrease the size of this surface resolution to something more reasonable, like 100. And I'm just going to call this one GM Live and press OK. So you're probably wondering why the extents of our geologic model actually extended above topography. So although the boundary, if we expand out this geologic model, we can look right here, the boundary extends above topography. The topography, the surface that's in this topography folder, is a special surface. This surface acts as the air-earth interface. So it essentially clips anything that is above topography from this particular geologic model. And you'll notice that that's consistent with the majority of objects that you're going to be creating. So we've got this geologic model. We can drag and drop that GM into our project, and you'll notice that it's just kind of this gray volume of rock. If we press the legend right here, this gray volume of rock represents an unknown lithology. And the objective of this next task is going to be to construct representative surfaces for geologic contacts and then activate them, which will essentially cut the volume associated with that unknown volume of rock that we see right here and replace it with that representative geologic contact. So there are a few different surface building algorithms that we can utilize and leverage within Leapfrog. And I'll just quickly go through some of these. And you'll have access to this one as you're going through this process as well. So we got the different surface types in Leapfrog. We're only going to look at the core contact surface types, deposits, erosions, intrusions, and veins in this very quick demonstration. So we've got deposits, erosions, intrusions, and veins. Although they seem geologic in nature, it was designed that way, realistically, they're just building shapes. So deposits and erosions build surfaces from one set of contact points, either above or below the unit of interest. So if you choose to build a deposit surface from this red contact right here, and you use the set of contacts below, it will build a flat surface from these red and orange and red and yellow contacts along this particular trajectory. Leapfrog is using the FAST RBF, that's a radial basis function surface building algorithm, to build a best fit surface based on the input data points available. So it converts this categorical information to numeric information where we see a zero values, which represents the contact points associated with each one of these drill holes, and builds a contour associated with these zero values. So it builds a best fit surface. So deposits and erosions construct the exact same geometries, flat surfaces along one set of contact points, but they behave quite differently. So deposit surfaces lay on top of anything that's underneath them, whereas erosion surfaces cut through anything that's underneath them. So we've got a depositional surface at the top that lays on top of a depositional surface that's underneath it. Where if you build an erosion surface, this erosional surface will actually cut through that depositional surface that's underneath it. The next step is an intrusion. So intrusions are great for building round bodies, especially in areas where you have maybe some salt or some volcanic intrusions, or if you're just trying to define like very thin lenses of sedimentary sequences. So this builds from one set of contacts above and below the unit of interest. So if we were to define this yellow unit, and we were to build an intrusion around this yellow unit, it takes the top and bottom contacts and fits this with a circular surface. So this is the process from converting from categorical to numeric. Again, it's using that fast radial basis function to build a best fit surface around the contacts associated with this interval. And that builds a surface represented by this yellow circle on the side right there. And finally, we have a vein surface, and a vein builds tabular bodies. Similar to how those intrusion surfaces worked, a vein will build a tabular body along the top and bottom of intervals. So instead of a circular, this one has a tabular body that extends to the boundaries of your model. And there's a ton of different ways that we can optimize how these surfaces are built and constructed and visualized. But again, we won't have time to get through every single detail within this quick session. Perfect. All right, so I'll actually take you through the process of constructing some of these surfaces and activating them. If we right-click Surface Chronology, we can create a new deposit or new erosion. In this case, I'm going to create an erosion surface from base lithology. So just to repeat, expand out your geologic model, right-click Surface Chronology, and press New Erosion from base lithology. We can work from top down, bottom up, or you can actually build each surface in whatever order you want. Generally speaking, I'll try and work from a particular direction of my geologic model, but there's each data set that you'll work with is going to be quite unique to the particular project, so you will have to sometimes go a bit off script. So this erosion surface dialog, this shows the primary lithology where we can define the primary lithology. And it also shows whether we choose contacts above or contacts below. So for this Lonja surface that we see right here in this tan color, we can see that it is the youngest unit associated with our model, so the unit on top. So if we choose contacts above, you'll notice that there are no contacting lithologies. If we switch and use contacts below, you'll see here that we now have 4 different contacts associated with this particular unit. So we've got 3 with this Pilagora, and we've got 1 contact with Lonja and Clostar Ivonage. So from these 4 contacts, it's going to build a best fit surface based on the overall trend and the contacts associated with these different geologic units. So we'll press OK, drag and drop this surface into the scene, and now we'll see that we have this surface constructed from these contacts. And there are multiple different things that you can do to optimize the structure of these surfaces, including double-clicking and turning, double-clicking the geologic model and turning snapping off. We can adjust the boundary filter if we're introducing faults into our model to create offsets. Snap to data basically means that the surface that you build snaps directly to the location of the contact, or some sort of polyline that you draw directly in this 3D scene. So there's multiple different ways that you can optimize how this surface is built. Probably one of the most useful ways is to apply an overall global trend. If you have some information about the overall trends associated with your stratigraphic sequences, generally speaking, unless there's some sort of massive fold or fault in your project area, stratigraphic sequences will generally be quite flat. So if you wanted to flatten out this surface, we can double click the logic contacts, go to trend. So I'll just repeat that, double click the contacts, go to trend, and we can apply a trend along a user-defined plane. So this stretches it in a particular direction. So we can use this plane drawing tool, this one right here. We can draw a plane that shows the overall trend that we expect this data to conform to. And we can set the ellipsoid ratios from this trend. So this is going to be a really quick overview of ellipsoid ratios, but we will send some content that explains this in detail. But in short, the ellipsoid ratios, the maximum and intermediate, are parallel to this plane. The maximum is in the direction of this green arrow. This is the pitch. You can see as we change this green arrow and we set from plane, the pitch also gets adjusted. Intermediate is perpendicular to this green arrow, but parallel to the plane. And the minimum is perpendicular to the plane. All surfaces that you build within Leapfrog are by default isotropic, which means that the ellipsoid ratios for a surface that you're going to build is by default stretched 1, 1, 1. Especially in areas where you have stratigraphic sequences, you may want to apply a trend to flatten this out in a particular direction. So this is where you can apply some anisotropy to do exactly that. So we can apply these ellipsoid ratios and we can essentially flatten this surface out. So this stretches this surface in the direction of that plane. And the process of constructing this 3D geologic model, in this case, if you're going to follow along in this particular, in this direction, is to work from top to bottom. But again, you can go off script and you can start to construct surfaces however you need to construct them. So we're going to work from top to bottom. Next, we'll choose this Bilagora, and we'll choose contacts below. So we're going to construct another erosion surface. So we'll right-click, surface chronology, new erosion from base lithology. This time we'll choose Bilagora. We'll use contacts below, and we can see that this contacts close to our Ivanich 4 times. So we'll press OK, drag and drop, left-click, drag and drop that into the scene. Double-click, and we'll actually apply the exact same trend. A dip of 0, dip azimuth, and a pitch of 90 is essentially just flat. So you can use that user-defined plane, or if you wanted to just flatten your surface out horizontally, you can use the default direction of that plane. So we'll change the ellipsoid ratios from 5, 5, 1, and then that flattens that surface out. And again, we'll kind of work from top to bottom. So I'll pick up the pace a bit because this is a recorded video, which you can play back as you're actually constructing your own conceptual model. Well, new erosion from base lithology, close star, use contacts below. We've got these 5 contacts with this gray unit. Press OK, drag and drop, double click, go to trend, and we'll flatten this out with the 5, 5, 1 trend. And we'll do this one last time using this gray unit with the pink unit. Right click, surface chronology, new deposit from base lithology. We'll choose the gray unit, use contacts below, and we can use these 5 contacts again to construct the contact associated with the gray and the pink unit. Actually, I'm going to adjust that, and I'm not going to use that orange unit, and I'm just going to use the pink. Sorry, I'm going to delete that one. I went a bit quick. So I'm going to repeat that process. I'll right-click new erosion from base lithology. I'll choose the gray unit, use contacts below, and I'm actually going to ignore that orange unit for now. Press OK, drag and drop. Check out the overall trend associated with this unit, double click, and we can flatten this out in the same way that we flattened all of the other units out. So although we have these surfaces that are representing the different geologic contacts, you'll notice if you drag and drop your geologic model into the scene, that it is still this unknown volume of rock, even though we've defined the contacts associated with each unit. So the way that Leapfrog works is these surfaces that represent geologic contacts have to be activated in order to generate volumes associated with each rock type. The algorithm, or the way that it works on the back end, is essentially these representative surfaces will cut holes in this unknown volume of rock, like we see right here. So this is going to replace this unknown volume of rock. It's going to apply some Boolean logic to replace that hole that this surface cuts out with the representative rock type associated with the surface. So to start activating these surfaces and building volumes, we can double click the surface chronology, which is going to define the Younging direction or the cross-cutting relationships associated with each object. Objects or geologic or surfaces that are higher up on this list will take precedence over surfaces that are lower on this list in areas of overlap. So we're going to change this. We're going to move the Younging direction to ensure that the units that we're going to be working on are correct. So we've got Longit on top, we've got Klostar, Bilagora, Ivanich to Klostar, and Moslavaca to Ivanich. You can activate these all at the same time, or you can activate them one by one. For the sake of this quick demonstration, I'm actually going to activate them one by one, just to show you how this Boolean replacement process works on the back end. So if we press OK, and we activate that one contact associated with Ivanich or the gray unit and the pink unit, you can see that the volumes associated with this geologic model now correspond with the units that we've activated. And we'll work from top to bottom again. We'll activate this second surface. And now you can see that the surface associated with this red and green unit has been activated. So anywhere underneath that surface shows gray. Anywhere above that surface shows red. And we'll do the exact same thing for each geologic contact. So in this scenario, we've constructed a 3D geologic model from drilling contacts alone. But you do have a lot more information within your project. Let's look at just one of these seismic lines, and there's multiple different ways we can do this. So I would suggest to reference the online learning material and devise your own way if you wanted to construct and interpret and adjust the geologic model that you generate based on any kind of geophysical data. So let's look at one of these geophysical sections, LOH. And we can see that this kind of cuts through the middle of our model. Actually, let's look at maybe a different one. Let's look at this one right here, LO6. So I'm only going to show one example of this, but you can use geophysical data like seismic data to inform the structure of the surfaces that you generate from drilling contacts away from these drilling contacts. So this seismic data you can see conforms to a structure along this particular trajectory. And as we see, this contact kind of dips steeply because it's only being informed by essentially 5 different drilling contacts. We can utilize the structure of this geophysical grid to adjust the structure of this surface away from data. So if we look at the CloStar, the red and gray surface right here, if you wanted to inform that surface away from data, and again, there's multiple different ways we can do this. I'm going to turn off all of the other units. I'm going to turn on the red and gray surface. We can right-click, go to project tree, so it's this one right here. This surface can be adjusted using a polyline. So we can right-click, and this allows us to essentially draw our own interpretations in 3 dimensions, which is going to adjust the structure of not only the surface, but then the associated volume. So we can right-click, edit with polyline, and we can adjust the structure of this surface with a polyline that we draw directly in 3 dimensions. Using a polyline that conforms to the structure of this 3D surface. We'll press save, and then that surface will then update based on the structure of this polyline. So I went a bit quick there, so I'm going to delete this interpretation, and I'm going to replay that, and I'm going to focus on some of the intricacies associated with the polyline drawing process. So if you wanted to adjust the structure of the surface, you can simply right-click on the surface that you wanted to adjust and press Edit with Polyline. You have a few different ways that you can do this. You can either draw directly on a 2D slicer, which we looked at before, or you can draw, the 2D slicer, which we looked at visualizing and stepping through our model. So you can draw directly on that 2D slicer. Or if you have a 3D object that you wanted to draw on, you could also draw directly on a 3D object. To activate the polyline drawing tool, you can press this Draw Lines button. And now you can see on the screen here, we have a crosshair with some, with a little note icon to the bottom right of it. So we got a crosshair here. As we step away from 3D objects, because we have this 3D object drawing enabled, you can see that there's no object under the mouse. So for this particular polyline, we do have to have an object underneath it to draw this polyline. Now, from this input seismic data, you can construct multiple different interpretations. So generally speaking, the way that seismic data can be used within this particular workflow is to inform your interpretations away from drilling contacts. So in this scenario, you might actually think that as you go away from this drilling contact, it actually dips up quite a bit. And if that's the case, we can start to construct this surface by left-clicking and conforming to the structure of these of the seismic lines. Once you're finished with this particular interpretation, you can right-click and right-click one more time, spin around, and then you can use this again to visually QC how you expect this interpretation to be constructed. One really important thing to consider is that polylines have polarity and directionality. So depending on the plunge and azimuth that you draw this polyline in, this will force that polyline in that particular direction. The default viewing for polylines is actually quite small. So if you wanted to expand this out to, again, visually QC the interpretations that you make, you can left click in the properties panel and we can increase the ribbon width to something quite a bit larger. So this increases the ribbon, which shows us the polarity associated with this polyline, and also the cone, which shows us the direction. The tangent cone can be adjusted by left clicking the tangent cone or the directionality of this tangent cone and pressing A, that's A as in Alan, on your keyboard. So if you left click this cone and press A, you can see that the directionality of this polyline gets adjusted. I'm going to turn off that seismic line shortly. We also have to consider the polarity. So each one of these polylines has polarity. There's a positive and a negative side. When you digitize them directly from your surfaces, the colors will represent each geologic unit. If you double click the green line, whoops, I have to zoom in. If we double click the green line, there you go. If you double click the green line, this will select all of the portions or the segments of this polyline, where depending on the direction that you digitize these polylines, you may need to switch the polarity. So if you switch the polarity, this shows red on bottom, gray on top, where if you're creating a stratigraphic sequence where red is actually in the real world on top and gray is on bottom, if you inform the structure of this surface with a polyline with the reversed polarity, you can get quite interesting results. So if we were to save this and register that into our polyline building tool, you can see that this has been totally flipped on its head. Whereas if we were to construct this, we can select all and adjust that. If we were to construct it with the correct polarity, with red on top, gray on bottom, this informs the polyline with the correct information, or it informs the surface with the correct information. I did see a question come in if we can draw on multiple objects, and the answer is yes. These polylines are 3D interpretations. So the workflow here, if we wanted to focus again on this red and gray unit, let's pull in another one of these contacts where we see the structure of this unit likely comes along here and down. We can continue adjusting this polyline. Actually, I'll probably close this polyline and show how you can continue to adjust it. So if we were to close this drawing and remove it from the 3D scene, this surface still has that polyline on it. So we can drag and drop, visualize it. We can right click this polyline and we can edit. And this allows us to continually edit this in space. So we can again activate the 3D cursor, and this is going to be a bad interpretation. Don't worry about that. And we can again continue to construct this surface in 3 dimensions. So you can have multiple crossing polylines, and the workflow that will likely support in this particular scenario is to use each seismic section to construct and inform the surfaces associated with each geologic contact away from data. So we've adjusted this surface with these 2 new polylines that are drawn on this particular object, and if we press save, you can see here that the structure of this surface conforms to the polyline associated with the drawing on this 2D seismic section and this drilling contact. So it informs the surface, which then informs the volumes. And that is a very quick demonstration in how you can construct and create 3D geologic models. It's not just about creating these nice looking figures for your different geologic units. These units can also be used as containers to propagate physical properties out. So I'll show you 2 examples of how we can create 3D physical property models. If we expand out the drilling information, we can drag and drop our temperature logs into the 3D scene. So last data is incredibly highly sampled. We've got a sample of probably every 10 centimeters along the well track, which creates thousands and thousands and thousands of points, which for the example here where we're looking at temperature logs might be a bit overkill. So Leapfrog also enables you to upscale 3 physical property values. So we can right-click the upscale tables, and we can create a new numeric points upscale over the entire well. And I'll just repeat that. Right-click, upscale tables, new numeric points upscale, and we'll go entire well. The upscaling length, again, this is a really quick demonstration, so I won't have time to cover all of the details associated with each parameter. But we'll go to output columns, expand out well last points, scroll down, and we'll choose the numeric value that we wanted to upscale. I will actually cover this, sorry. This upscaling length shows the length so 10 meters essentially, and this is going to average the values associated with each 10-meter interval along the well track with a minimum of 5 points. So all of this very densely sampled data sets will be averaged along an interval of 10 meters, but there has to be a minimum of 5 points associated with it. We'll press OK, and now we can see that instead of point values here, we now have intervals associated with each 10 meters. So you see here the interval, the downhole depth, and the averaged temperature value. So to construct a 3D temperature model, you can construct it from the last points that you see right here, but the algorithm is going to take quite a long time to process because there's thousands and thousands of points. Or you can simply upscale, which is going to average the values associated with each interval. But because there's less data to interpolate, it will be quite a bit quicker of a process. So you can upscale any of the information that you see right here in the last points file. We can expand out the numeric models, right-click numeric models. You have multiple options, including a multi-domain RBF interpolant. This is going to allow you to essentially block the interpolant values between the volumes that you've created in your geologic model. Or you can use the new RBF interpolant, which is a global solver, which is going to, again, create kind of like best fit isosurfaces based on the input data that's available. Just looking at time, we won't have time to cover the multi-domain RBF interpolant, but there is content available that will walk you through the process of creating that. So we'll create a new RBF interpolant. We'll choose the numeric values that we want to interpolate. So in this case, we'll choose temperature associated with the numeric points upscale. We can decrease the surface resolution to something more reasonable, again, like the geologic model, something like 100. And similar to the geologic model, we have a boundary that's extended out to essentially cover all of the data associated with our project. Generally speaking, when I'm working on a project, I like to make sure that everything is kind of contained within the same area. So I can enclose an object in the middle right corner of this interpolant boundary, and this is going to automatically adjust this interpolant boundary to the 3D object that I enclose. So if I press enclose object, I press Control, Shift, and left on my keyboard. So Control, Shift, and left. This is going to automatically collapse all of these. You can also press this button right here or that one. I'm going to expand out my geologic model, go to GM Live, expand out boundary, and this is going to automatically adjust the boundary to the easting, northing, and elevation extents defined by my geologic model. So we'll press OK, and then in this temperature 2, we have some isosurfaces from statistically significant portions of our model. And I'll quickly show you how you can adjust this RBF interpolant, leaving about 10 minutes for questions. So if we double click the interpolant that we just generated, the first step is likely to adjust the outputs. So depending on the isosurface that you're most focused in, we can go to the, so again, sorry, I double clicked the temp 2, went to the outputs tab, and I'm going to add new isosurface values. So you can double click and adjust the isosurface values right here. So we can adjust this to 60, 85, 100. And if you wanted to add additional isosurface values, you can add more by pressing this plus button. So we'll add another one at 115, another one at 130, and another one at 145. And we'll press OK. And we can drag and drop those in. And now we have a much wider breadth of the temperature ranges associated with the values that we used to interpolate between these drill hole objects. Again, this is an RBF interpolant, but you will have access to multi-domain RBF interpolants and also linear geostatistics, which again, we won't have time to cover today. One of the greatest things about Leapfrog is the ability to quickly create multiple realizations of the subsurface. So this is the default temperature distribution without adjusting anything, any of the trends available. So similar to how we constructed our geologic model and we had multiple iterations of that geologic model, we can do the same thing with our temperature profile. We can right-click temp and we can create a copy, and we'll call this one temp to linear, or sorry, maybe we'll apply a trend to this one. So we can clear that scene and we'll look at the isosurfaces associated with this second temperature model. We can double click and there's a few things that we can change here, including applying a global trend, similar to how we can stretch our geologic contacts in a particular direction. We can also apply a trend to stretch this interpretation in a particular horizontal direction. We can also change the interpolant. So we can change it from a linear interpolant to maybe a spheroidal. We can change it from a constant drift to a linear drift. This help file right here will guide you in which drift and interpolant, sill, and base range is best suited for the data type that you're working with. Just as a quick example, I'll show you what happens if we change from constant to linear drift, where we've got this much flatter profile, and this could suggest that there's a temperature anomaly in the top left side. The difference between constant and linear drifts is away from data, the interpolation algorithm using a constant drift is going to decay to 0, whereas using a linear drift away from data, the interpolant will decay linearly. So you can look at the difference between these two isosurface values. And you can see that depending on the type of interpolant, drift, and trend that you use, you can create wildly different temperature distributions. And the last thing that I'll end off on, and I will run through this quite quick to leave some time for Q&A, is the ability to evaluate your geologic model and your physical property models onto discretized block models. So these blocks are essentially geocellular grids. So we're constructing 3D property distributions and 3D geologic models that have volumes and surfaces, but to enable calculations, which is going to be incredibly important for estimating, like potential temperatures in particular different geologic units for plugging into your spreadsheets and machine learning algorithms. We can create a new block model, regular block. We'll enclose an object, and we'll enclose again this geologic model live. We'll change the size of our blocks to 100 by 100 by 100. We can see here in the back end that this is adjusting, and we can adjust the evaluations. So we'll evaluate, so we'll go to the evaluations tab. We'll evaluate our geologic model and our numeric model onto this block model. And now we can see the entire 3D temperature distribution for each block and our geologic model. And if we right-click our geologic model, we can press the calculations and filters option. We can press this little circle with a star inside of it, and we can create a new numeric calculation. We can call it whatever we want. For this quick example, I'm just going to show you how to extract information about the temperature in a particular unit. We can insert, pressing insert, in window, and we can write an if block. So this shows if, and we left click our geologic model equals a particular unit. Let's just say this pink unit right here. So if geologic model equals this pink unit, then we'll return the results from temperature 2. Otherwise, we'll return a blank. And I realize that this is quite quick, but this is just a quick overview to give you some inspiration about some of the things that you can do with this calculator. If you drag and drop this object in the scene now we can look at the temperature distribution that's constrained within that unit that we've defined. And finally, the planned wells that we looked at before, the objects that we created in 3 dimensions can be evaluated onto these planned wells, which are the locations of your unknown wells by right-clicking and pressing evaluations, and we can evaluate temperature distributions and geologic units onto these planned wells. So this unknown 2, we can see the different geologic models that we generated, also the different temperature profiles. These can be exported as interval tables or points, which can then be fed into your either machine learning algorithms or compared to your machine learning algorithms. Perfect. All right. So Pavel, I think I probably went a bit long there, but we do still have 7 minutes for questions, but I'm happy to stick around a bit longer.
Yeah, that would be great. So there are a few questions. We'll just be going through them. First question is it possible to create a well correlation view with a Leapfrog?
Yes, it is, absolutely. It doesn't look like there's that many questions that came through, so I can probably actually just show them how to do that. Cool. All right. So the well correlation, if you expand out the well data folder, we can right-click the well correlation tool to build a well correlation set. Generally, I'll expand out the wells and drag and drop the location. So let's look at a well correlation between Viravitica 1 and Viravitica 3 alpha. So right-click the well correlation and press New Correlation. To set up the well correlation set, you press this little blue triangle. So these wells that are kind of connected with these blue triangles, this is going to bring us back into the 3D view. You have to click that little blue triangle again, which allows you to select wells, and then you left click and left click. You see a little 1 and 2. If you press save, this is now added the 2 different wells to your correlation set, where we can add any kind of categorical information associated with the well that we're looking at. You can press Alt and scroll to compress. So Alt, which is also shown right here, Alt and scroll down. And then you can start to add multiple different points associated with the drilling information. So you can simply just left click and drag from the project tree multiple physical property values to construct a well correlation set. If you needed to adjust the structure of the interpretations based on your well correlation, you can create a new interpretation table right here. So we can create a new interpretation table. We can copy from one of the original source columns. So we choose the strat simplified, which is what we built our geologic model off of. The initial data is going to be all intervals. We can call this interpretation table. So this is going to copy all intervals from this strat simplified, press OK. And now based on the input data associated with our project, where we can see, let's look at maybe density, density logs. So if you have a density log right here, and you have this particular interval, the interpretation table we can adjust to match any of the input logs, whereas the original strat simplified table we cannot adjust. So Leapfrog doesn't really like you to adjust the original raw data, but using this well correlation set, you can create a new interpretation table, which is essentially a new interpretation based on any kind of input, categorical or numeric information. Cool.
Okay. So next question is, can you go through opening the software and setting up the project coordinate system, units, etc.?
Yep. So that's a really interesting question, Jamie. Leapfrog is actually unitless and coordinateless. So we recommend that you do all of the GIS preparation outside of Leapfrog. This particular project, and I actually forgot to associate the metadata here. So you see a coordinate system on the bottom of Leapfrog, and this is essentially just metadata. So I used a GIS program to reproject all of the objects, drilling information, seismic lines, and topographical information to a common coordinate system for import and visualization and interpretation within Leapfrog. The coordinate system that we are using here is UTM zone 33 north, NAD 83. So if you did want to add additional data for whatever reason, it would have to be in that particular coordinate system. And the same thing goes for units. So Leapfrog treats things as simply ground units. It doesn't read the difference between meters and feet or inches and centimeters. Again, we suggest that you convert everything to a common unit before you import into Leapfrog. Same thing for like Celsius and Fahrenheit. It just simply reads them as data points.
Right. So next question is, when you select an anisotropic trend on your erosion surfaces, how you're picking in which direction you select your 5-5-1 trend?
Yep. So for interpretation purposes, the plane that I drew was basically just on the basis that sedimentary layers are generally deposited in kind of like a flat way. But if you did look at this data, so if we looked at this data right here, and you visualize it like this, you can see that there is kind of a trend that kind of goes this way. So it might have actually been more accurate to set a trend that may be more representative of something like this. But the trend is simply a tool that you can use to construct the geology the way that you think it should be constructed. So again, I would suggest playing with a couple of different things, making a few different iterations of your model, and then choosing the best one or choosing multiple different iterations to either plug into your machine learning algorithm to use as a basis for calculations or multi-domained RBFs. So there's multiple different ways that you can do that, and I simply chose a flat surface because it was a very quick demonstration.
All right. So we have another question from Julian, coming probably as continuation of the question on the horizons. What about the faults? How can we model those surfaces?
Yeah, we didn't have time to cover faults today, but it would be a very similar process. I don't think that we'll have time to cover that, but there is information associated with faulted modeling in the online manual that we'll send out. But basically, faults can be picked using polylines, the same way that we pick the different geologic contacts. Surfaces can be constructed using those polylines or GIS lines at the surface. Faults can be constructed in a number of different ways, but the way that faults work within Leapfrog is it splits your model up into two different structural domains. And that basically splits that RBF interpolant into, again, two different structural domains, which then creates offsets associated with your units. If you look at a lot of the seismic lines, it doesn't look like it's a heavily faulted area, whether or not that there's faults that are fluid conduits, but there doesn't seem to be a ton of offset within a lot of the seismic lines. So I would suggest to review the online training material if you wanted to start to implement faults within your geologic model, but based off of a quick look on the seismic data, it doesn't look like there's many large faults that would produce large offsets within your geologic units. But right. Yeah, if you wanted to just like represent a fault with a mesh, it would be quite easy to construct that using a polyline.
All right. Another question is if the logs of wells with seismic section / line in a scene window can be seen.
Yep. So if you have a seismic section like this and you wanted to see logs associated with your drilling information, you can drag the graphs object and we can choose, maybe let's choose the density logs. And we'll increase the scale and we'll change to a color. That's maybe a bit better. Gamma ray might actually be the best one. So we'll choose an offset, we'll increase the scale, and we'll change it to black. So this is a way in 3 dimensions how you can start to relate your seismic data to your logged information. Unfortunately, at this time, increase the scale again. So here we've got gamma logs associated with the seismic, and you can display this against your log lithologies. At this time, we can't add seismic data to the well correlation tab, but that would be quite a nice feature. So currently in 3 dimensions, we can visualize your log lithologies with your well log information and your seismic as a backdrop.
All right. And the last question so far is how we will get access to the software. I'll go ahead and say that's probably going to be a separate email.
Yeah, it'll be a separate email. So step number 1 is actually registering on the Discord chat and creating a team. So you can't have access to the software until you have a team created. So I guess that would be call out number 1. Once you have that team created, the fantastic team at the SPE Geothermal will let us know which teams and which individuals on those teams need access to the software, and then we'll get you all set up.
You create a team and want to add another member. Go ahead, add another member. They're going to receive their copy.
Excellent. And as we're just wrapping things up, please feel free to reach out with any questions you might have. We do have another session number 7, I think, on Wednesday at this same time. So 7 a.m. Pacific. Pavel, what time is that UTC?
Oh, I believe it's going to be 3 p.m. UTC.
Perfect. And that one is on heat flow modeling, I believe. Is that correct? Heat flow quantification.
Yes, heat flow.
Yeah. So that should be an absolute stunner of a session. I'd highly recommend attending that one. And in the meantime, I guess enjoy the rest of your evenings. I'll pass it back to Pavel. Thank you so much for the attendance.
Thank you to you for the presentation. I'll be closing the session now. Thank you everyone for attending.
Thanks, everyone.